It's a great pleasure to welcome my scientific son. I guess Bob normally has the honor to introduce the speaker, but Bob is somewhere enjoying his life. So I got the honors. So Young is G5 plus student. And has done beautiful work in quantum diamond mechanics that I'm looking forward to see again today. All right.
Okay.
Go for it.
Thank you, Marco. It feels so great to be a scientific son of Marco. So today's topic I'm going to talk about is the engineering the solid-state qubits by using micro-electro-mechanical systems. So before I start, I'd like to talk about, actually yesterday I thought about this whole day about the philosophy of today's talk. Because let me tell you, so now as you've heard, I'm a senior student, a grad student here. Also I have a separate master's degree, so which makes me older. But so when I was a first-year student, I oftentimes, I was working really hard, but oftentimes I used to forget to be honest, what the motivation of the work is. I mean, I put some stuff on the motivation slides during my group meeting, but that's what I just learned from senior students. But I used to forget my true motivation, and sometimes I jokingly used to say that maybe I should write that Marco asked me to do this rather than putting real motivation. That idea was never executed, but over time, many years of experience, I realized that I actually started understanding better and better about this phrase, you're standing on the shoulders of the giants. So to really understand why I'm doing this, why I work on this, I started looking at other fields, which is a bigger field of my own field. So that brings us to this outline of today's talk. So I start from this big field of quantum technology, which is very popular these days. And then after brief introduction, I goes down to the specific part of the quantum technology, which is a quantum network. And then I go down to the system I actually worked on, which is a solid-state emitter, which is very useful for building quantum network. And then, so my actual work is about what kind of challenges exist for solid-state emitters, and also how we engineer to overcome this problem. So let's start with the overview of this entire field. So now quantum technology has become a buzzword, and like all kinds of people want to work on it. And to my mind, actually, I think at the moment, there are three big subfields exist, which is, of course, the biggest one is probably the quantum computer. There's lots of startups going on, Intel, Microsoft, IBM, a lot of startups, Google, things like that. And another application of quantum technology is the quantum communication, which is provably secure. So if someone tries to eavesdrop on what you're communicating, the moment they try, actually you realize that they're doing. And so recent work from research lab in China, they actually did the quantum communication through the satellite. And final one is this is what Harvard groups, especially Professor Jacobi group is working really hard on, is quantum sensing using a quantum system that, so these days I heard in academia so probing the spin structure of the material using the nitrogen vacancy center is becoming very popular for scientific research. But today's talk is more focused on probably lots of quantum computer and probably a little bit of quantum computation together rather than quantum sensing. So let's go dive into the hardware implementation of the quantum computer. So there are lots of different ways to make the quantum computer. These are different platforms out there. So let me start with the first one, which is a superconducting qubit. So this is what Google and IBM are doing. So their working principle is that they use this thing called the Josephson junction, which is a sandwich structure. You have a superconductor, 1 nanometer of insulator, and another superconductor. With this structure, you can make artificial two-level system, which is the artificial atom in a macro scale. So that's why this field got so popular and developed fast, because you can engineer and fabricate the atom you want. That's a superconductor qubit. And ion trap is that so you have a bunch of ions that has a charge, and you can actually build a trap to those ions side by side, like make a 1D array, and then you can probe it optically. That's the ion trap. I think it's kind of at this moment, it's like a runner-up of this entire technology. And the third one is also recently becoming popular, is a gate-defined quantum dot, which is you put electrode and apply voltage, and then that makes the artificial environment of electric field, and you can capture electron there. And that electron works as the quantum bit. And the last one is the optical quantum computing. That is like there is a leading group in University of Bristol that you can make integrated optics, and then I don't understand fully very well yet, but they can only use a linear optical components to do a quantum computation. So so let's say we already have built quantum computers, and then you have these components. And how can you do better once you have some certain size of quantum computer? Eventually, you're going to have some size of the quantum computer, and how can you do better after that? That's where this quantum network idea comes in. So you have two quantum components. So that's schematically shown here from this paper, a highly cited paper, famous paper. That so this each block is called a quantum node. It's a separate quantum system, and then you bring independent two systems. They can be the same physical platform or different platforms, but you can connect them, and then you can make it more powerful, because the power of the quantum computation comes from putting more bits together. It's not like this scaling is nothing like a classical computer. A classical computer you used to use 32-bit and now 64-bit, but quantum computer gets exponentially powerful as you add more and more quantum systems. The problem is making this connection is very difficult, because you have to connect it in a quantum way. That is called the entanglement. So when you make two things connected in a quantum way, it's called entanglement. So let me briefly explain what entanglement means. So this picture represents two electrons. You can think of electrons as small magnets. So if you bring two small magnets, and then let's first look at, so this arrow represents the north and south pole. And let's first look at this unentangled state. This is a quantum state. And this is electron A, and this is electron B. So in this case, electron A is spin up, electron B is spin down. So you can say, OK, this is up, this is down. That's it. So there are like separate electrons. But in quantum world, you can actually make this kind of state. It's actually called the Bell state, which is a superposition of this. Actually, this is wrong. This, yeah, this should be gone. Sorry. This and that are superimposed, such that. So what happens is that. So in this case, let's say you measure the spin of the electron A, and then. So according to Copenhagen interpretation, it will collapse to one of these. Let's say it collapses to the first term. You observe the spin up of electron A. And then whatever you do later, if you measure electron B, it's always spin down. And if it collapses to this state, vice versa. The problem is these are correlated. If you see something in A, it has to affect electron B. So this is the nature of the entanglement, and this is where the wonder resides in, because these two electrons, if they're entangled, if you put thousands of kilometers away, they still work. It's intuitively very wrong, because two electrons are 1,000 kilometers apart, and they use something, you do something here, and then it affects something that's 1,000 kilometers apart. That's the wonder of the entanglement, and then this is the key of the quantum computation. And then making this entanglement in practical devices is very challenging. So Easiest way to build this is to put two Gibbs right next to each other. So if you, for example, if you put electrons like just 1 nanometer away, they'll just start feeling each other's magnetic field because the spin will generate magnetic field. So spin electron A feels the electron B is there, and B also feels electron A is there. But what if they're very far away, and then if you want to make them entangled, make them feel each other? That's where this solid emitter comes in. Solid emitter, the solid state emitter comes in. The solid state emitter, its biggest benefit is that it has an interface with the photon. So what you can do is you can entangle, for example, if you have some kind of color center in this is actually Marco's work, the diamond nanowire. So if you have some color center inside the wire, and then if it shoots the light, you can make it in a way that the light is entangled with the electron spin of the color center. And then that light can go like tens of kilometers away and meets another color center, and it can transfer that entanglement into another color center. So you can entangle two quantum systems kilometers away, tens of 100 kilometers away. So that's the power of the solid state emitter, and that's why people are studying this. Let me go into solid state emitter a little bit more. So this is the fluorescence image of the color center of the diamond, and solid state emitter is usually a simple point defect. So for example, the NV color center, which is studied a lot, is made when you take out 2 carbon atoms from the diamond lattice and replace it with a nitrogen atom like this. And then this local defect behaves like an artificial atom by capturing electrons, and it has these discrete energy levels. And then it has an emission around 640 nanometer. So we have an interface with the photon and its electronic state, and it also has electronic spins. And there are other kinds of quantum dots, indium gallium arsenide, and then they can be also controlled by electrically, and also talks to photons, things like that. So bottom line is these solid state emitters talks to the light and also buried inside the solid. And the benefit of the solid state emitter is you can realize by comparing to a conventional system. So as I said, solid state emitter behaves like an artificial atom, and one can ask, why do you just not use the real atom? The problem is a real atom is hard to deal with. Real atom is really good, but it's hard to deal with. The problem is the trapping. The atom is unlike even like ion trap is like very powerful because ion has charge. You can apply electric field and you can just like trap it. But like atom it doesn't have charge. How are you going to trap it? There are ways to do it. For example, Lukin group is working very hard on it, and they recently made an array of like 50 atoms. But still, it's quite challenging to put the atom in a precise position that you want. But in case of solid state emitter, what happens is that it's already trapped inside by the solid. It's just there. So your sample of the solid piece. So then what you need to do is just like put it in under the microscope, and then you can shoot the light there and control it. You just need this thing called a confocal microscope just to get a better SNR, but basically it's a microscope. Another good thing about solid state emitter is that it's very small. It's atomic size, and because of that, you can put many of them in a very small volume, which means it has the potential for scalability. You can put billions of them in a very small area. And the next one is actually, this is what our group is focusing on, is that another benefit is you can fabricate the device. So these days, nanofabrication is developing more and more, such that you can build the device around the location near the color center, such that you can actually start affecting its property. So basically, you can engineer the property of the color center by building the device around it. So these are all benefits of the color center. So far I've been talking only about good things, but in real life, there's always a challenge. And then from here, I'm going to talk about what's the real challenge in this system. So let me talk about the general challenge in a quantum system. This applies to all kinds of quantum systems, not just to solid-state emitter. So fundamental challenge of all quantum systems is this. So basic building block of quantum computer is a single qubit. Single qubit means you make a superposition of two separate quantum states. So basically, if you superimpose two separate states, it evolves over time with the velocity with this like E1 energy over h bar, and then E1 and E2 are different, and then they have this evolution over time, and then these pictures represent this evolution. The problem is, in real system, and unlike this equation actually just like oscillates forever, but in real system, there is always this exponential decay. And that's called a decoherence. Decoherence basically means how long you can keep your superposition alive. And the reason for the superposition is destroyed is because it interacts with the environment. So your environment is not super stable. So there is always some fluctuations in the environment, and it destroys the coherence, or basically superposition of your qubit. So the challenge is, for all quantum systems, is how long you can keep your coherence, how long you can keep your superposition alive. So the answer is the isolation. You just detach it from the environment as much as possible, best you can do. The problem is it, again, imposes a fundamental challenge of control, because you always want to control your qubit to do some useful calculations. So, and that control also happens to has to be a quantum level. So which means it has to react to a very small energy scale, such as single photon, single phonons, things like that. So to do that, your quantum system has to be super sensitive to your energy domain. For example, if your control is electric field, your quantum system has to be very sensitive to electric field. But that gives a good control. But if your environment has some electric field fluctuation, then it's going to destroy the coherence. So there is this fundamental problem. You need a good control, you need a high sensitivity, but you also need a good isolation. So that's why making quantum computers is so difficult. And the right answer is just like you isolate it from everything, like as much as possible, like kill all the noise sources, and then just like make a pure signal of your control. That's the way to go for quantum computers. And then to be more specific on solid-state qubit, I'll go through all the fluctuating environment examples. So here I put two figures, which is, so in this case, the quantum system is a nitrogen vacancy center. So this work is from this reference that showing the ground state to excited state optical transition. So this bright red light it represents a transition, optical transition. And in case of NV, what happens is that, so it has like this ground and excited states, and whenever there is an electric field fluctuation, for example, you have NV and you have some kind of charge trap here, and this charge trap gets electron in and out like in some time scale, and whenever it happens, it feels a different electric field, and in this ground and electron excited states, their spacing changes, it jumps. That's what you're seeing here. So their transition frequency, all of a sudden it jumps, go back and forth, it goes crazy. It's called spectral diffusion. So in this work, what they were doing was that they were trying to give a feedback to stabilize it. But this represents the challenge in the electric field fluctuation. The second one is magnetic field fluctuation. So this is relevant to the spin. So spin is basically, as I said, it's a magnet. So if you put a magnet in a bath full of like randomly rotating small magnets, and then fluctuations of these things can affect the spin of the nitrogen vacancy center. So in case of nitrogen vacancy, it can be, depending on how you grow the sample, it can be nitrogen impurity electron spins in diamond, or sometimes it can be a carbon-13 nucleus spin. And then that's known to kill the coherence of the nitrogen vacancy electron spin. So these two were electric and magnetic field, but in case of a solid state emitter, there's another fluctuating mechanism, which is a lattice vibration. So, if you have a solid, it has this crystal structure. It has a regular array of atoms, and then these, if you think about it, these are mechanical structure. So it actually supports these normal plane modes. And then it's known that there are, in the bulk structure, it's always has this longitudinal or transverse phonon modes, which can be represented by this dispersion plot. And then what happens with this kind of motion is that whenever this like acoustic wave passes by your color center, it moves the atom like this way and that way. And if your color center is here, actually it can feel its atoms jiggling. And the way it works is that because this thing is trapped inside the crystal, its orbital is affected by its structure nearby. So that vibration always happens when your temperature is not 0. So then that's usually a thermal fluctuation, and it's out of your control. It's really random. You can't kill it without going to 0 Kelvin. And the second one is that when you grow your sample, if you have a solid, your solid environment, so this is on the scale of like a few millimeters, like 2 millimeters, that each spot on the sample actually has a different stress environment. So for example, spot here, NV might be elongated this way, and NV here might be elongated that way, which makes this NV and that NV actually not the same thing. It's not like the real atom. Real atoms are exactly the same. You cannot distinguish them. They're fundamentally the same. But in case of the solid-state emitters, actually they are different because they're stretched in a different way. So here is the example of what you see. This is like optical spectroscopy with the NV centers at different locations, and they have their transition frequencies are different by a few gigahertz because they are feeling different strain. So that's another challenge that that these solid-state emitter systems have, because oftentimes you want to make you want to work with the exact same solid-state emitters and indistinguishable photons. Indistinguishable photon means at least their frequency has to be exactly the same. So from here, I'll go over how we approach this problem one by one. So let me first introduce the system we are working with, which is called the silicon vacancy color center, which has this structure. It's also in diamond, which has this structure. So these black ones represents carbons, and red one is a silicon atom, and their vacancy is split into half here and there. So it looks like this, and it has, according to group theory, it is called D3D symmetry, which has actually strong relevance to its characteristics. So SIV has become popular because it has some good optical properties, which are listed here. The first one is it has a large zero phonon line, which means whenever it makes a transition between ground and excited states, it's not always this like direct transition from here to there. Sometimes it involves lattice vibrations, which is called phonons, and it can absorb or emit phonons. And when that kind of a transition happens, its coherent property gets destroyed. So that's not the transition you want. So the clean transition without any phonon involved is called a zero phonon line, and you want this thing as big as possible. So in case of SIV, that number is about, so that the proportion of SIV zero phonon line is around 70 or 80% compared to 4% of NV. So that's the big benefit of SIV. And another one is that a small inhomogeneous distribution. So as I said, in a solid state environment, each color centers are slightly different. but that difference is relatively small compared to other solid-state emitters. And also, it is known that its optical transition is relatively stable, even for a long time, over like an hour of observation. It doesn't fluctuate or change it very fast. So here's a brief introduction of electronic structure. So all you need to remember is it has two orbitals at the ground state, two orbitals at the excited states, and then this 2x2 combination gives four optical transitions. And then if you do the spectroscopy, you get these 4 distinct lines, A, B, C, D. And then, so from here, let me go over how this system can engineer all those challenges, 4 challenges: electric field, magnetic field, and electric field, magnetic field, lattice vibration, and inhomogeneous distribution. All those challenges can be mitigated by using this system. So first of all, so left side, this picture is showing how its optical transition is stable over time in case of SIV. So this SIV is known to be very stable, especially when it is compared to nitrogen vacancy center. And that has a lot to do with its structure. So if you can see here and there, this is nitrogen vacancy, this is silicon vacancy. So their biggest difference is that silicon is in the middle rather than going to the side. So that actually brings a fundamental difference, because in case of nitrogen vacancy, it has a permanent electric dipole, which means so you have this dipole plus and minus charge. If you apply electric field, the distance changes. And then whenever there's a fluctuating environment, electric field, your plus and minus charges fluctuates like that. But in case of a silicon vacancy, because of this symmetry, this structure, it doesn't have the permanent dipole, at least to the first order, such that whenever it is like immune to a much less sensitive to fluctuating electric field environment. So SIV is, by nature, it's strong against electric field fluctuation. And the second part is the magnetic field fluctuation, so which is relevant to the spin coherence. So actually the very reason why color centers in diamond is popular is because of the maturity of the diamond material technology. So diamond is all made of carbons, and if you grow your sample very, very well, you can isotopically purify the diamond to have almost carbon-12, 99.7%. And so if you do that kind of engineering compared to natural abundance of carbon-13, so carbon-13 is the killer for the spin because it has a spin. Carbon-12 doesn't. So if you kill carbon-13 as much as possible, this is like spin coherence. You go from this black to red figure, which means you can make your spin very, very good. So diamond material engineering actually can give you a very good environment for a spin bath. So now what's left is lattice. That's the focus of our work. So let me tell you what SIV, what kind of opportunities you can get with SIV. Let's start with this inhomogeneous distribution. So as diamond, so from here to there, it has a different environment. But in case of diamond silicon vacancy, it is known that it is very, very responsive to external stress, which means you have two SIVs, like with a different transition frequency like that. And then you locally apply the stress to one SIV only, like to here. And then you change its transition frequency like that, and then bring it together and make it identical. That's possible because SIV is responding very well to stress. So that gives an opportunity for SIV to generate indistinguishable photons. But that's an opportunity, but at the same time, we run into this fundamental challenge again, the fundamental challenge of control and isolation. Because it's so sensitive to the strain, so if there is a like uncontrolled fluctuating lattice vibration, then it actually destroys your coherence time, so which is the case for SIV spin. So SIV spin, if you compare its coherence time with the NV center, so NV center is known to have about an order of microsecond at room temperature. But SIV center, even at 4 Kelvin, it is measured to be, so here is bottom is the measurement, measured to be about 40 nanosecond at 4 Kelvin, which is significantly lower than natural vacancy center. And it connects to this plot that it is too sensitive. So these thermal phonons are killing SIV spin coherence. And so here it comes our approach. So we want to engineer this problem using a mechanical structure. So to give you a brief introduction of the mechanical system, is we use this system called the MEMS system. It's basically all about making mechanical structure at the small scale using semiconductor fabrication technologies. The same fabrication can be applied to MEMS as well. So you make a mechanical structure, and then you put some electrodes around it to control its motion and also read out its motion. That's the MEMS technology, and it's scalable, it's very mature, it has been studied for many decades. For example, like these kind of projectors, you use the technology from MEMS, and also your Wii controller also has an accelerometer inside that uses MEMS technology. So adapting this technology to our system, we make this kind of device. So what we made is this. So this dark area actually is a single crystal diamond. And we make this cantilever structure first. Then there is a way to make silicon vacancy color centers at the specific locations, and we put electrodes around it. This bright part is gold. Then it has this kind of a capacitance-like structure that when you apply a voltage, this coulombic force attracts each other, and you can bend this cantilever structure. And when you bend the structure, it actually induces a stress inside of the cantilever that you can engineer the environment of the color center. And here's it's showing how we can place silicon vacancy at the location we want. It is as precise as on the order of 20 nanometers. By using focused ion beam technology, basically you can accelerate the silicon plus ions to a particular spot, and then you can do a subsequent annealing to turn it into a silicon vacancy. So here is the summary slide of how the fabrication is done, which we put a lot of effort to arrive here. So we first start with we do etching, regular etching, and then we tilt our stage. So this is oxygen plasma assisted ion milling. We tilt the stage and etch at an angle by rotating our sample stage, and then it effectively etches at an angle. So we end up having this suspended structure. This is how we make the cantilever, and then, as I said, we use focused ion beam to generate silicon vacancy color centers. And here is the detail of the electrode process, and we end up having this kind of structure. So here's the result of our device. So first of all, as I said, the first challenge was that these emitters are different, right? Because their environment of stress is different. Here we're showing how we can tune this optical transition into each other by applying voltage. So sorry, this is missing. So silicon vacancy is actually there. You can. The stress is actually a tensor component. It's a little bit complicated, but in this case, you can decompose into two different types. One is the transverse strain, which is applied along this plane. So you stretch the silicon vacancy like this. And another one is an axial strain. So you stretch or compress the silicon vacancy like up and down. And so from the group theory, you can predict how it will respond to the stress. For example, if you apply a transverse strain, it is known that each pair of ground and excited state orbitals, they split up. And in case of the axial strain, their ground and excited space, they move together. So this is the result of spectroscopy that's showing each of these. And here is the plot of how much we can, showing how much we can tune the optical transition frequencies. So in our case, the device performing the best, we could make so ground state splitting, which is about 50 gigahertz. So this is actually a very relevant number from silicon vacancy. We can change this from 50 gigahertz, which is a number you can get without any stress, and you can apply a stress and make that 50 to 1,000 gigahertz. That's what's showing here when we apply 600 volts across 4 micron. So so the amount of the shift in the transition frequency, it's much, much more than inhomogeneous distribution. So inhomogeneous distribution means when you don't do anything, if you look at different bunch of silicon vacancies, it's statistically, it has some kind of standard deviation. So that number is typically around, I think, like 5, 10 gigahertz. And then with our system, actually, we can tune like at least more by an order of magnitude, actually much more, about 2 or 3 orders of magnitude more, like 100 or 1,000 gigahertz, such that if you have 2 emitters, their transition frequency far away, it's easy to bring them together into same frequency. And the next part is how we fight the lattice, uncontrolled lattice vibrations, which is thermal fluctuations. Here, I need to go a little bit into detail of why that's happening. So in case of silicon vacancies, spin coherence, the coherence time is, as I said, it's limited by thermal phonons. This is why it's happening. So when you use the spin qubit, actually you use this part. So what you do here is that you apply a magnetic field, and then each orbital, as a Zeeman splitting, you go spin up and down. And then, so 4 orbitals split into 8 orbitals, and then 8 levels, and then you choose the bottommost one, the pair. And then you can use this as a spin qubit, and the coherence time of this spin qubit is known to be limited to 40 nanosecond. And the physics involved there is that this gamma term here. So from here, from within the ground state orbitals, from the bottom branch to upper branch, it is very, very sensitive to lattice vibration. So whenever there is some vibration at the corresponding frequency, it can do a resonant absorption of the phonon. And then your orbital can jump from here to there. And that moment, actually, its coherence gets destroyed. And then this, so at a finite temperature, there's always thermal phonons. This fluctuation is stochastic, it's out of control. And then whenever that tends to happen every 40 nanoseconds. So that's why it only has 40 nanoseconds. So our approach here is that, so as I said, this absorption process is resonant. So this vibration has to match the frequency, which is, without any stress, it's 50 gigahertz. So if you have a way to manage its 40 gigahertz up to like higher frequency, what happens is that at a fixed temperature, the occupation of the thermal phonon number drops rapidly if you increase the frequency. That's what's shown at the right figure here. So you can just look at this blue curve. Blue curve is the product of these 2 red curves. So what happens is that as you increase this corresponding spacing, number of thermal phonons actually has this trend. It goes up and it starts going down. So at a higher frequency, h bar omega becomes much, much larger than kT. Then there is no thermal occupation. So there is no fluctuation. And the thing is, we have, with our device, we have a control knob to achieve this by applying the strain. So our experiment is very simple. We apply a strain by putting some voltage at like different voltage levels. And at each voltage levels, we measure the coherence time of the spin directly. So here is the scheme for measuring spin coherence time. So what we do is, as I said, we apply a magnetic field, DC magnetic field, and split it up to like 8 levels. And among those 8 levels, we choose 3 different levels, 1A, 1B, and 3B. And this is called, in quantum optics, it's called the lambda scheme because it looks like lambda. And what we do is we shoot 2 lasers with different frequencies, C1 and C2. By doing that, we can measure its spin coherence time. So there are a lot of ways to measure spin coherence time, but a particular measurement we're doing is called coherent population trapping. This is, I think, probably the simplest method you can do because you can do everything optically. So what happens is that if you have a lambda system, so like you have 2 ground system and 1 common excited state, you shoot 2 lasers. What happens is that your energy eigenstate, if you do an analysis of an energy eigenstate with the existence of the photon, which is an interaction term, you can have this dressed state picture, which is now your energy eigenstate is not anymore 1 and 2. Your energy eigenstate becomes superposition of 1 and 2 with a different sign. And I'll call it one is non-coupled, another one is coupled. The reason for the name is coupled system. So if you do analysis, it responds to the photon such that there is an oscillation between coupled and the excited states. So whatever that's staying here, so if your state starts from here, there is a chance that it definitely goes up to 0. After it goes up to 0, what can happen is that it can either go to non-coupled or coupled. So there are like equal chances. And but once, let's say, by chance you get to by chance of 50%, you end up being a non-coupled state. What happens is a non-coupled state doesn't couple to these other 2. So once you get there, it's just a trap there. You don't get out. But like if you are here, you always like light pumps it up, and then you always eventually end up getting non-coupled state. So that's why it has a name called coherent population trapping. Also, your population will be eventually trapped here. So experimentally, what you do is you fix this omega R1 and you scan this omega R2. When this omega R2 is exactly resonant with the 0 and 2, this kind of system happens, and everything is here. So you don't have any population at 0 because everything is here. It doesn't like get pumped up. And your signal, fluorescence signal, is basically proportional to your population of the 0 state. So you have this kind of signal. So that everything is trapped in this case. And it has this dip. And the way you measure the coherence is to see the width of this dip. The reason is that there is always some small leakage between non-coupled state and coupled state, and that is proportional to the coherence. So by looking at the width of this dip, you get that is a function of the decoherence rate, plus also is a function of a laser, but it's technical details. So here is the final result of our coherent population trapping measurement. So we start with this dip. This is the dip of the coherent population trapping. So you can see it has some width. And as you go down, we apply more and more stress such that you split up the spacing between 2 ground state branches. And then what happens is that its coherence time gets better and better, which is revealing by these dips narrow down as you apply the strain. So the width of this dip, there are 2 dips for some reason. I'll explain later. And then if you map out this dip at this bottom figure as a function of ground state splitting, which is proportional to the stress, your CPT line width gets narrowed until it gets saturated at this point, which means that our spin coherence time gets improve until it hits some limit. So in this case, this limit turns out that, so if you compare this number to the measurement done by Looking Group lately, so this number is actually what they get with a very low, much lower temperature measurement. So this saturation means that we're not limited by the mechanism I explained, this resonant absorption of phonon anymore. Now we are in the regime, at this high strain regime, we are limited, spin coherence is limited by some other mechanism. So our device can reach that regime. And this is a figure that's explaining why we have two dips. Basically, we rotate a DC magnetic field and see the spacing between, we saw the spacing between these two dips, and it has this trend, and it can be explained by assuming there's another spin nearby at a reasonable distance. So that's pretty much of our result, and here's the outlook of how this project can go even further. So this picture is I got from this reference, which is a good review paper of all the different quantum systems. And as you've seen, there are many different physical implementations of quantum systems. And the thing is, each system has its own advantages and disadvantages. So what you want to do is you want to bring advantages together and combine them. That's the spirit of this quantum network. You want to make use of the best of each system. If you make an analogy with the classical computing system, so for example, classical computer system does the exact same thing. For example, if you have a DRAM and your solid state drive, your solid state drive works without any the supply of voltage, but it's slow. Your RAM always needs a voltage, but it's really fast. So it's the same thing. So in case of the quantum system, your CPU can be superconducting qubit, which can calculate things very well, but its memory time is very limited. But in case of spin is its computation with the spin is like much less developed compared to superconducting qubit. But for a system like SIB or natural vacancy, their storage time is much longer. Their coherence time is better than superconducting qubit. So you can imagine this kind of system that you have a CPU, quantum CPU made of superconducting qubit, and then you have a silicon vacancy color center spin nearby on the same chip. And then you make the connection between CPU and this memory. I'll call it quantum RAM. Let's say silicon vacancy is a quantum RAM, and you make a coherent interface. The strength of the silicon vacancy color center is that typically it's really hard to make a good interface with the spin, because actually it's all again linked to the reason why spin is a good memory, that spin is such a small magnet. So it's a very weak magnet. So if you want to control it, you have to send a lot of power to like flip it. But sending a lot of power is not necessarily a quantum way. So you have to send a very small power and still should be able to flip it. So it is well known that it is almost impossible to use magnetic field control to do a quantum control of the single spin. So what can you do? The one way that is being pursued right now is using spin orbit coupling, which is instead of using magnetic field, you send electric field, and you shake the system's orbital, and then this orbital is actually linked with the magnetic field. Basically, by sending electric field, you can generate an effective magnetic field, and you can control the spin. That's the one way it can be done. And another way I'm proposing here is you can do the same with sending acoustic wave. So as I said, silicon vacancy is very sensitive to like lattice vibrations. So what you can do is you can send the acoustic wave to silicon vacancy spin, and then so if you work out the numbers, actually it looks quite promising for silicon vacancy that it can couple to a phonon, single phonon in a quantum way, basically. And acoustic wave is already demonstrated that it can couple to many other quantum systems, including superconducting qubits. So silicon vacancy is a probably promising platform to realize this kind of interface between superconducting qubit and silicon vacancy electron spin via acoustic wave. And another picture is the once you realize this kind of memory, and if you want to build your system even like bigger, like let's say you want to link your quantum CPU in this still fridge to another dilution fridge, you have to get out of this cold temperature, and you can do it with making a link with the optical fiber like this. This is also part of the work, our group's work, collaboration with Misha Lukin's group, that you can place silicon vacancy in the photonic crystal, which is the optical cavity, and you can make this coherent interface with the photons. So in summary, so I want to emphasize these 4 points, that the reason we work on solid-state emitter is that it is really important building block for a long-distance quantum network using photons. And the challenge, as is the case for all the quantum systems for solid-state emitter, is the fluctuating environment, which includes electric field, magnetic field, and lattice vibration. And our system, the silicon vacancy color center, is actually dealing with all of those challenges by using our MEMS device. And yeah, so outlook of this this platform is that silicon vacancy spin is, as far as I know, its response to the lattice vibration is the strongest among all known color centers. So it has some potential to make a coherent interface between spin and acoustic phonons. So I'd like to thank my colleagues who worked together on this project. I want to single out these Srujan and Ben, who worked closely with me entire time on this project. And I'd like to appreciate my advisor and also other PIs and the funding sources. Thank you for listening.
The silicon vacancies are in silicon crystals?
No, they are in diamond
They're
crystals.
in diamond?
Yeah.
So when you say high strain,
Yes.
like what are you talking about? Like how high a strain, like percentage?
Yeah, that's a good question. So strain actually...
You can't strain diamond.
Yeah, so strain is actually unitless quantity. So let me go here. Here, yeah. So they're in diamonds, and
Right.
so they are actually stretched like this. So strain, the way you measure strain is so without any stress, right? You have a perfect crystal, and then if you stretch it by like 1%, so strain number is 0.01. So delta L over L is the definition of strain, yeah, although it becomes a tensor. So with this device, the level we can reach is about 10 to negative 3. Basically, it's 0.1%.
Exactly.
Yeah.
And you're doing that electrostatically?
Yeah, electrostatically.
What are we talking? Like 500 volts? Like
yeah, we went up to 600 volts. I have, sorry.
Does it ever arc or like?
Yeah, so we had a lot of troubles in the past, actually. So the thing is, yeah, it's like this. It looks like this. So it has an electrode here and there. So their distance is on the order of 3 to 4 micron.
With like half a kilovolt across there.
Yeah, so yeah, with half a kilovolts. Yes, the reason why it doesn't get destroyed is first of all, it's in the vacuum. So there is no no Townsend breakdowns.
Yeah.
Yeah, but there are all sorts of other problems that I actually used to fail a lot of times with the gold. And then I looked into why this is happening, and then there is always small leakage current. I don't know. I think it's going through the surface, so it tends to destroy this gold. Gold is very fragile, actually, especially at this high field. So I replaced the material to a tantalum, which is a very high evaporation point. So basically, whenever these electrodes get destroyed, eventually it's all the Joule heating. You have a very high heating at local spot, like hot spot, and then it just like gets burst and evaporate, melts, whatever. So that doesn't happen to a material with a very high evaporation point. And I looked into the material that's allowed in CNS, and the metal with the highest evaporation point you can evaporate is tantalum. So we went with tantalum. And then it worked, yeah.
Good work.
Right now, is the vacancy, silicon vacancy, the bond, it's aligned with a certain crystal direction matters?
That's right. So it looks, yeah, it looks like, sorry, it looks like this. So it looks like this, such that basically these are carbons, right? The black ones are carbons. So it has a half vacuum up and down. And if you connect these two half vacuums, it's like one direction in diamond crystal. Yeah.
It's matter. So it's able to control how this align. Or
So
only
yes,
align certain direction, it can
yeah,
the property.
exactly. So you can see how it can be controlled here. So this is the sample we make. So if you think about the way we make the sample is this top surface is like what you get with your substrate, your sample. Your sample has a face, right? Yeah, that's fixed 1, 0, 0, 1. But this 1, minus 0 and 1, 1, 0 direction is under your control. You can do a rotation of your GDS file. Yeah.
But you don't control silicon vacancy mutation. You have 4 possibilities and then you look at different.
Yeah, exactly. So in this case, actually, I am using these 4 arrows to represent 4 possible orientations there. Yeah. Other questions?
None? All right. Well,
Okay.
then, thank you.
Okay.